Hi everyone, I'm Yu-Peng Chen, a PhD student from University of Florida. Today I'll be presenting our study on investigating contextual notifications to drive self-monitoring in mHealth apps for weight maintenance. We integrated insights from interoperability literature into a mobile health context with guidance from two health experts on our team. Meena, a registered dietitian with 21 years of research experience, and Dr. Ross, a faculty member in clinical psychology with 17 years of experience in obesity treatment. Weight trackers offer self-monitoring to support health behavior change, yet maintaining consistent self-monitoring over time proves challenging for users. Push notifications can help increase users' app engagement, but they are often ignored due to poor timing. To address this challenge, we turned our attention to the field of interoperability, which aims to find the best moment a system can interrupt people. Extensive research in this field has shown that when compared to notifications sent based on a fixed time, sending notifications based on contextual factors such as time of day, location, and current activity can reduce perceived disruption, decrease response time, and increase click rate. However, when researchers in the field of mobile health apply this concept to support users' health behavior change, there are mixed results. Therefore, we look at how the timing of notifications influence the user's interaction with notifications and their self-monitoring behavior. More specifically, our independent variable is the timing of notifications with two conditions, context-based or time-based. Informed by previous research, we used two contextual factors. First is time of day, for which we ask the user to set their daily schedule for 4 categories. Second, we use Google's transition API to detect transitions between these 5 types of activities. Time-based notifications were sent based only on the user's daily schedule at fixed times, while context-based notifications were sent based on both the user's daily schedule and physical activity transitions. We built the GatorTrack app for our study. The first screenshot is how a push notification from GatorTrack looks like. The second screenshot is the home page of GatorTrack along with an in-app notification. The third screenshot is the weigh-in page for the user to input their daily weight. The fourth screenshot shows details of the user's calorie consumption. We recruited 30 participants. All of them are Samsung phone users because the Google's transition API only works on Android phones and performed the best on Samsung phones based on our prototype testing. All participants ranged in age from 18 to 54. There were 20 self-identified males and 10 self-identified females. 18 participants had experience with mobile health apps, while 12 did not. We conducted a within-subject study for 4 weeks. We counterbalanced the order effect by having 2 groups, each with 15 people, so they either start with context-based for 2 weeks and then switch to time-based for another 2 weeks, or vice versa. As you can see, we also conducted an onboarding meeting and 2 interviews via Zoom. Next, I will describe the design of our intervention and the 2 types of notification. We consulted health experts on our team for selecting key self-monitoring data points required for weight maintenance, which are weight, lunch, dinner, physical activities, and self-rated measures of weight-related variables. For example, asking the user how hungry they are. For each type of data, we implemented a corresponding notification. For the first 4 data types, we asked the user to log at least 1 item every day, and the daily notification was sent if the data was still missing by the scheduled notification time. For questionnaires, we sent 2 notifications every week. Therefore, users had 8 opportunities for filling out the questionnaires and 112 opportunities for logging the other 4 types of data, totaling 120 logging opportunities, and thus 120 opportunities for the app to send a notification. We further brainstormed with our health experts to design the timing of our notifications based on the user's daily schedule, which we asked them to set during onboarding and allowed them to change it at any time during the study period. Our app sends time-based notifications for each data type at a fixed time that's decided by shifting the user's daily schedule by a specific duration as shown in the table. Let's look at an example. If the user sets their wake-up time at 5:30 a.m., we add 10 minutes to it and send the weight notification at 5:40 a.m. Here's another example. for the questionnaire notification that was sent based on the bedtime. For context-based notifications, instead of sending at a fixed time, we designed a time range. And then within this time range, if there's a transition detected and the transition type matches, we send the notification. So it's dynamic based on the user's current activity. Let's again look at an example. A wake notification corresponds to the wake-up time. If the user set wake-up time at 5:30 a.m., we start detecting for transitions 30 minutes before that, so that's 5 a.m. And then we stop listening for transitions 2 hours after the wake-up time, so that's 7:30 a.m. Within this time range, if there's no transition detected, we'll keep listening. If there's a transition detected and the transition type matches, we send a wait notification. We call this a transition-triggered notification. In a case where no transition was detected during this time range, we still sent a notification at the end time to make sure that a notification was always sent if the data was still missing, and we call that a timeout notification. To capture the user's interaction with the notification, we designed 3 flags that indicate the status of a notification. A notification could be sent, clicked, or completed. Let's use this flow diagram to illustrate. The smiley face represents the scheduled notification time. If the data is already logged before that time, no notifications will be sent. In this case, the sent flag will be false, and naturally the clicked and completed flags will both be false. In the case where the data is not logged before the scheduled time, a notification will be sent, so the sent flag is set to be true. After a notification was sent, we make it disappear after 16 minutes to capture the timely effect of notifications. Within the 16 minutes, the notifications could be clicked, and in that case, we set the click flag to be true. The notifications could also be completed. We define completing a notification as logging the data associated with the notification. If the corresponding data was logged within 60 minutes after a notification was sent, the complete flag will be set to true. So far, I have outlined our motivation, research questions, and study design. Now let's delve into the findings of our study. I will present the effect of notification timing on 4 dependent variables. First, we'll look at the overall log rate to capture the user's daily self-monitoring behavior. We define the overall log rate as the count of daily logs for each data type, divided by the number of total logging opportunities, which is 120. As you can see in the graph, although the average log rate is slightly higher in the context-based condition, which is the orange box, there is no significant difference between the 2 conditions in how frequently users logged. For the next 3 dependent variables, we'll look at the user's interaction with notifications. We define the response time as the time difference between the time when the notification was clicked and the time when it was sent. We found that in the context-based condition, users clicked notifications significantly faster. We then looked at the click rate, which we define as the number of click notifications divided by the number of notifications that were sent. We found that in a context-based condition, users clicked notifications significantly more often. But reacting to notifications faster and more frequently does not necessarily mean that the user also tracked data more. And remember that our ultimate goal is to enhance self-monitoring behaviors. So that leads to our last dependent variable, which is the completion rate. We define the completion rate as the number of completed notifications divided by the number of notifications that were sent. Remember that a notification can only be completed within 60 minutes after it was sent. We use this measure to capture the direct effect of notifications on tracking behaviors, and we call this timely self-monitoring. We found that in the context-based condition, users completed significantly more notifications. This means notifications timed around the user's activity transitions improves rates and promptness of timely self-monitoring. Next, I'll talk about 3 discussion points of our study. The main finding of our work is that contextual notifications can trigger timely self-monitoring. Why is this important? Because the weight management literature recommends that, in general, people should log their food and activity throughout the day, meaning as eating and/or exercising occurs, versus waiting until the end of the day to log. The benefits are threefold. First, it helps with timely self-reflection, which provides opportunities for the user to adapt their meal or exercise for the rest of the day to achieve daily goals. Second, logging data when eating and/or exercising occurs addresses the recall bias of human memory. Third, accurate timestamps of when the target behavior actually occurs have the potential for training predictive machine learning models that can enable real-time personalized health services. For the second point, remember that although we found a significant result for timely self-monitoring, there is no significant difference in the overall daily self-monitoring behaviors between our two conditions. To take a closer look at these results, let's break down how logging could happen in the user's daily life. There were three scenarios. First, the user could log before a notification was sent. Second, the user could log after a notification was sent and before it disappeared after 16 minutes. Third, the user could log after a notification disappeared. We can see that while the completion rate captures solely the second scenario, all scenarios contributed to the overall log rate. Thus, we looked into the interview data that helped uncover individual differences in tracking behaviors that could potentially explain why our contextual notifications were not effective in overall log rate. First, for the case where the user logged before receiving a notification. For this scenario, some participants mentioned that after participating in the study for a while, they developed a habit of tracking right away and did not really think about the notifications. Next, for the case where the user logged after a notification disappeared. For this scenario, some participants mentioned that they prefer to log everything at the end of the day. Some mentioned that their strategy was to remember the task and do it afterwards, while others mentioned that they would leave the notifications unread in the panel and address them later in the day. Based on these insights, we conclude that there's still room to improve overall self-monitoring behavior. Lastly, recall that we used two contextual factors for sending our context-based notifications, time of day and physical activity transition. For this discussion point, we dig deeper into the effect of each contextual factors. As a reminder, we factored in time of day by creating a time range based on the user's daily schedule, and send a timeout notification if there was no transition detected by the end of the time range. If a transition was detected within the time range, we send a transition-triggered notification. We found that among the completed notifications, about 61% of them were timeout notifications, while about 39% of them were transition-triggered notifications. This suggests that there was more contributing to logging behaviors than purely activity transitions. We further looked at the effect of these two types of context-based notification on completion rate. Remember that when compared to purely time-based notifications, context-based notifications triggered more timely logging events. However, when we compared only the context-based timeout notifications with the purely time-based notifications, there was no significant effect on the completion rate. Interestingly, when we compared only the context-based transition-triggered notifications with the purely time-based notifications, we found a significant effect on the completion rate. This result suggests that even though transition detection didn't perform as well as we thought it would, as shown in the lower number of these transition-triggered notifications, they played a significant role in triggering more timely self-monitoring behaviors. Thus, future work could consider exploring better ways to capture transitions. Here are the three takeaways regarding our contextual notifications in weight management apps. First, they trigger more timely self-monitoring behaviors. This has an important design implication for future weight trackers. Second, they triggered faster and more frequent responses. This echoes prior work on using contextual notifications that increase user app engagement. Lastly, there's still room to improve the overall self-monitoring behaviors, which are implicitly but not directly influenced by the notifications. With that, I wrap up my talk. This study is a collaboration between the Health Promotion Lab, the Ruiz Lab, and the INNET Lab at UF. Thank you for listening.